Okay, so here I go with my v sub x vectors. Now in the y direction, we have a little bit of a different situation. So at time t0, we still don't have any vertical velocity. But at time t1, we've got a vy equal to negative 9.8 meters per second. At time t2, we have a vy equal to 2 times that, or negative 19.6 meters per second. Time t3, we have a vy equal to 3 times that of negative 29.4 meters per second. And after that, a vy equal to negative 39.2 meters per second. So you see that as we continue in our projectile motion, that gravity continues to accelerate our cannon or change its velocity every second by a factor of 9.8 meters per second. So the important concept depicted in this is that the horizontal velocity remains constant during the course of the trajectory, and the vertical velocity changes by 9.8 meters per second every second. Now let's draw something a little bit different. So let's illustrate what happens when the cannon is now fired at an angle. So we'll give ourselves a couple of points in time. Okay, so here's my v sub x. And here is v sub y. Now let's say that we had an initial v sub y of 19.6 meters per second. We'll just make it easy for ourselves. 19.6 meters per second. Notice it's positive. Then, 1 second later, it's smaller. Vy is now 9.8 meters per second. Right here, Vy is 0 meters per second at the peak. Okay, this is super important. Vy is 0 here at the peak. Pay attention to that. Okay, so the next second after the peak, here we are in the downwards direction. Negative 9.8 meters per second. Negative 19.6 meters per second. Negative 29.4 meters per second. And on and on and on we go. Okay, so again, horizontal velocity remains constant during the course of the trajectory, and the vertical velocity changes again by 9.8 meters per second every second. Okay, so in the case of looking at the projectiles fired from the boat, and here's boat A, here's boat B, and one of them had a path like this. That's a terrible parabola, I apologize. And the other was like this. And our conclusion from the boat extra credit problem was that VIY affects the time in the air, t, when fired at the same time And for these two, delta y is the same. Now we can actually take a look at that and see how it's illustrated in the PhET app. So let's switch on over to the PhET app. So here we go. We're going to fire our cannon first at, actually I'll fire it at the higher angle first. Okay, so my initial speed is 18 meters per second. I'm going to fire first at a high or a large angle with a large VIY, and then I'll change the angle and fire with a short VIY. Change it to slow. Okay, so it's easy to illustrate on the PhET app, which is why I really like this. You saw how when we launched the steeper angle first, and even though we launched the steeper angle first, that cannon still hit the ground after the cannon that was launched with the smaller angle. So we launched at 30 degrees, and I think we launched at around 70 degrees. Now this is different than asking how we maximize, and I think this is where some of you got confused. We also asked a question in class, how do we maximize delta x? This is the question that you want to answer with 45 degrees, because in the 45, 45, 90 right triangle, we have sides of root 2 over 2, which means that Vx and VIY are both maximized. Now this is important for us because if you look at the equation for delta x equals V sub xt, we want to maximize Vx, sure, that's obvious. So we want V cosine theta to be maximized. But delta x also depends on t, and t is maximized when V sine theta is at a max. Okay, remember, sine has to do with the vertical, cosine has to do with the horizontal. If this is our total velocity, then V sine theta is VIY and V cosine theta is Vx. Okay, but at 45 degrees, we're maximizing both Vx and VIY. And delta x is dependent on both of those. So when you're maximizing delta x, not t, you want to maximize both the cosine and the sine of the angle. Okay, both the cosine and the sine of the angle. Now just to review how this applies to our equations, in our y direction, we have delta y equals VIYT plus 1/2 gt squared. Vfy squared equals VIY squared plus 2g delta y. And Vfy equals VIY plus gt. Now remember, anytime you see delta y, this is a y final minus y initial, right? Y final minus y initial. Now in the x direction, we only have one equation that makes any sense, and that's delta x equals vxt. So when we're resolving our velocity vectors into the components, you would plug those resolved vectors in here, v cosine theta, and here, v sine theta. Okay, so unless something is launched completely vertically or completely horizontally, that means it's launched something like this at an angle. So you need to resolve. Resolve that vector into its components. Now one last thing I want to cover in this really quick recap video are just the graphs for projectile motion. So in the x direction, we have constant velocity, so a constant rate of displacement, which means for our x position graph versus time, we are constantly displacing. So see how the slope here is constant, meaning the velocity is constant. So velocity in the x is constant. Now position in the y in meters looks a little different. Remember that the shape of the trajectory is represented by the position of the projectile in the y graph. Okay, so the y position graph will have the same shape as the actual path that the projectile takes. So in projectile motion, the y graph again will mimic the trajectory of the projectile. Okay, so for projectile motion, that is the y position. Now on your homework, we were looking at something that didn't have a full, wasn't a full parabola, right? I think the object in your homework was shot off the edge of a cliff. So it was something that was projected with just an initial horizontal velocity and then it fell towards the earth, similar to our first Canon example. So I think this was in the homework. And so your graph for position had to look something like this. Okay, it looks something like that. Now remember, velocity in the y is increasing, so the slope of your position needs to be changing, which means that the position graph will be curved. And the y velocity continues to increase in the negative direction. Okay, so again, we'll check the trend of our slope. Here the slope of the tangent line approximates 0. Then it gets increasingly more negative. When we look at our y values here on the velocity graph, it starts at 0 and it gets increasingly more negative. So we're okay. Okay guys, so that was a really short recap of all of the important parts of the chapter and most of the key points, but I'll also post a video after this of some solved problems for you to follow. So hope you have a great night and I will see you guys soon. Bye.